Okay, yeah, thanks very much. So I'm going to talk about a formalization project that I've been working on for about a year. The setting for the work that I'm describing is homotopy type theory. The formalization uses cubical Agda. Okay, the impetus for the project was a 2024 preprint by Michu and L and Reed Barton. There, they introduce a family of variants of the axiom of countable choice for higher toposes. In the preprint, they investigate the relationship between these axioms and other properties which may or may not hold of higher toposes, such as hypercompleteness and Postnikov completeness. In the preprint, they observe that some of their definitions and their proofs are fit to be translated into homotopy type theory and formalized. So now there's a formalization of a chunk of their work in cubical Agda. I'm going to say a little bit more about exactly what's been formalized at the end of the talk. Something that I think is maybe worth highlighting is that one thing that we have now as part of this work is proof in homotopy type theory that any one of these forms of the axiom of countable choice implies the existence of an infinity truncation modality. What is an infinity truncation modality? I'm going to spend the first half of the talk trying to explain what this term means. So I'm trying to explain what an infinity truncation modality is. I'm going to start by defining connectivity. Connectivity is a very familiar concept in homotopy type theory. One way to define connectivity is inductively. So type is called -1 connected if it's merely inhabited, meaning if we can prove that it's non-empty, but we can't necessarily produce a point. And so that a type is n+1 connected if it's merely inhabited. And for every pair x and y of points in the type of proofs that these points are equal is n connected. This definition differs a little bit from the definition in the HoTT book, but they're equivalent. The inductive definition is due to Kokand. Okay, a map is called n-connected if all of its fibers are n-connected as types. Next is truncation. Like connectivity, truncation is very familiar, well-known basic ingredient in homotopy type theory. Type is called n-truncated if it's right orthogonal to all n-connected maps. What this means is that whenever we have an n-connected map from C to D like this, the type whose terms are pairs consisting of an arrow like this from D to X, making a triangle, and a proof that the triangle commutes, this type of pairs is contractible. That's what I mean when I say right orthogonal. For each n, now there's a modality which sends every type X to an n-truncated image of that type. This is the n-truncation of X. It's written like this. It'll come up again. This satisfies a universal property. There's a map from X into its n-truncation. That map will come up again. Okay. I should say, should maybe go back. All right, sometimes for some n, we already know what an n-truncated type is, but just under another name. So -1 truncated types are propositions, 0 truncated types are sets. We might say propositional truncation instead of -1 truncation. We might say set truncation rather than 0 truncation. Okay, so we've discussed n-truncated and n-connected types where n is finite. Now we can move on to the infinite case. A type or a map is called infinity connected if it's n connected for all finite n. Then, like you'd expect, a type is called infinity truncated if it is right orthogonal to all infinity connected maps. Again, being right orthogonal means the type consisting of arrows like this and proofs that the square that the triangle commutes is contractible. Okay. How much time is there? I think I might skip the intuition. What? Would you like the intuition?
Yes.
Okay. All right. So these conditions are actually very natural. If X has a point, then we can define the kth homotopy group of X, pi k of X at the point like this. This is the sphere. This is set truncation. We saw homotopy groups on Tuesday. Also, F is a map from X to Y that preserves the point. Then we have a function between pi k of X at the point and pi k of Y at the point. A map is called n-connected if for all X and all k less than or equal to n, pi k of F is an isomorphism. So that's equivalent to the definition that we saw before. All right, similarly for n-connected maps now for all k, so no bound on k anymore. A map between n-truncated types is an equivalence if and only if it's n-connected. A map between infinity truncated types is an equivalence if and only if it's infinity connected. So saying that a type is truncated is like a way to express how much can we learn about this type just by studying its homotopy groups. Gives us maybe an estimate for how many homotopy groups would we need to calculate before we understood everything about the type. Maybe don't take this too seriously. Sadly, we can't prove that all types are infinity truncated. This is independent of HoTT. It's a very famous principle that's independent of HoTT. So, I mean, amongst other things, based on this intuition, this means that like we can't learn everything about every type just by calculating its homotopy groups. All right, now infinity truncation. We would like to have a modality which sends every type to an infinity truncated image of that type, just like before we had the n-truncation modalities which sent types to n-truncated images. If we can construct something like this, we're going to call it the infinity truncation modality, right? That was the expression, that phrase that I had at the start that I said I was going to try and explain for the first half of the talk. This is where we are. Unfortunately, again, we don't know how to construct an infinity truncation modality in HoTT in general. We don't know that it can't be constructed. At least to my knowledge, we don't know that it can't be constructed. But we don't know how to construct it we don't know how we can construct it, at least if we don't make more assumptions. So now we're going to discuss some assumptions, some axioms that imply that we can construct an infinity truncation modality. This discussion of these axioms is going to occupy us for the second half of the talk. These axioms are all known to be independent of HoTT. We're going to make some comments about their relationships, dependence or independence relationships to each other. Each one of the axioms that we'll discuss implies that an infinity truncation modality can be constructed, and we'll explain how in each case. First axiom is hypercompleteness. Hypercompleteness, I sort of already mentioned. Hypercompleteness says that all types is the axiom asserting that all types are infinity truncated. If we assume hypercompleteness, then we can construct an infinity truncation modality. It's just a trivial modality. It sends every type to itself. We already mentioned that infinity truncation, the axiom of infinity truncation is independent of HoTT. The famous countermodel is the higher topos of parameterized spectrum, which you can Google if you want to understand why this is independent of HoTT. Before describing the next two axioms, we need a definition. A Postnikov tower is a sequence of types with maps between them. Looks like this. Not just any tower. The Postnikov towers satisfy a special property. The Postnikov towers are such that the kth type in the sequence is k truncated. The kth map in the sequence is k connected. Kth map, I mean the map whose codomain is the kth type. So here's the 0th map, here's the first map, here's the n-1th map, the nth map. If X is a type, we can use the n-truncation modalities that we saw earlier to construct a Postnikov tower. This Postnikov tower has for its types the n truncations of X. Sometimes I'm gonna call this the Postnikov tower of X. Sometimes I'm gonna call this X's Postnikov tower. Meanwhile, if we have a Postnikov tower like this, we can take its limit. We can construct a type, limit of which is the limit of the tower. So that's these two constructions, the construction of the Postnikov tower of a type and the construction of the limit of a Postnikov tower we're going to need for the next two axioms. Okay, second axiom, Postnikov convergence. There's a map from X into the limit of its Postnikov tower. This comes from the universal maps from X into the truncations of X, like this. Postnikov convergence says that this vertical map, this eta here from X into the limit of its tower, is always in equivalence. That's the axiom. That's Postnikov convergence. Postnikov convergence asserts that this vertical map is always in equivalence. Now, limits of Postnikov towers are always infinity truncated. There's a proof of this at the end of the slides, but what this means is that Postnikov convergence implies hypercompleteness, which in turn implies that an infinity truncation modality exists, and it's equal to the trivial modality. Again, okay. Something I'll come back to, there are examples of hypertoposes which are hypercomplete, but not Postnikov conversion. So, although Postnikov convergence implies hypercompleteness, these aren't equivalent. Okay, third axiom. Postnikov effectiveness. Given a Postnikov tower over here, we can take its limit, then we can construct the Postnikov tower off the limit, and then we can construct a ladder of maps like this, where all of these squares commute. The name for the rungs of the ladder is always epsilon. Postnikov effectiveness is the axiom asserting that all of these horizontal maps, all of these epsilons are always equivalences for every Postnikov tower. So epsilon n is an equivalence for all n for all a. Postnikov effectiveness also implies the existence of an infinity truncation modality. The function underlying the modality is this. It's the function that sends a type to the limit of its Postnikov tower. There are hypertoposes which satisfy Postnikov effectiveness, but not hypercompleteness. So we know that this modality is not always trivial. Finally, we have a non-trivial infinity truncation modality. Okay. Like I said, this is the function underlying the modality. Now, I said that limits of Postnikov towers are always infinity truncated. This means that everything in the image of this modality is infinity truncated. We need to show the converse. We need to show that if something is infinity truncated, then it's in the image of the modality, right? And then we know that this serves as an infinity truncation modality. We have one direction, we need the other direction. We're going to use a lemma. If Postnikov effectiveness is true, then for the ladder of maps we had before, all the way back here, if over here we have something that's already the Postnikov tower of a fixed type, then the inverses to the maps epsilon n, the maps epsilon n have an inverse. That's what we're assuming. That's Postnikov effectiveness. The inverses to the maps are the truncations of the eta map that we saw before. If we know that, there's a proof at the end of the slides. If we know that, then we can appeal to the following diagram to show that this eta here is infinity connected, because now this means that if X is infinity truncated, then this is already an equivalence. So X is already in the image of the modality. So that's all infinity truncated types are in the image of the modality, right? Because the diagram has, this is an n-connected map. This is an n-connected map. These are the universal maps. We know that they're n-connected. This is an equivalence. Now the truncation of eta is an equivalence because it's the inverse to epsilon n. And so we've factored eta through, we've factored an n-connected map through eta by an n-connected map. So we know that eta has to be n-connected. Okay. Last axiom, we're sort of getting up to time. Countable choice says that if we have a family of inhabited objects and the product is inhabited, Nell and Barton in this preprint dimension generalize this to what they call the axiom of countable choice for dimension less than or equal to d. This means that if you have, this means that taking a countable product decreases the connectivity of some types by at most d. We recover the original case, this case up here, when we set d to be 0 and k to be -1. They prove that all of these forms of the axiom of countable choice imply Postnikov effectiveness. They observe that their proof can be translated into HoTT and formalized. This has been carried out. The code is available at this link. The consequence of this is that, of course, now we know that these axioms of countable choice, because they imply Postnikov effectiveness, they also imply the existence of infinity truncation modality. Other things in this repository, as well as the proof that countable choice implies Postnikov effectiveness, that's Snell and Barton's proof. We have a proof that limits of Postnikov towers are infinity truncated. Proof that Postnikov effectiveness implies that eta is infinity connected. Proof that Postnikov effectiveness implies that this the map sending a type to the limit of its Postnikov tower is a modality. And that's basically everything I have to say. A few things to add to the formalization. The relationship between, I should note, this is for a reviewer who asked a question related to this. The relationship between infinity truncation and limits of Postnikov towers is very subtle. So this example of a topos which is hypercomplete but not Postnikov convergent is also gives us a situation where, like, because it's hypercomplete, infinity truncation is trivial, but because it's not Postnikov convergent, taking limits of Postnikov towers is not trivial. So limits of Postnikov towers and infinity truncation, they disagree. They can disagree sometimes. Yeah, thanks for listening. That's